Hello and good evening for this. This is the penultimate Wednesday of our organic chemistry office hours in the evening. I am here and available to answer any questions. I don't know if there are any out there. I actually checked my email earlier today. Didn't have any questions for Chem 420 office hours, but I'm rechecking right now. None in my inbox. Let's give Canvas a look. Oh, whoa, what up? Raj is in the house, which means we most likely do have questions. Yeah, was totally gonna show up. I was a few minutes late today because my wife got called in last minute to work an evening shift, and my 2-year-old's bedtime is 6:30, and my office hours are also at 6:30. So I was singing lullabies to him, and then set him all down, and then jetted down here to the office and started booting up the stream. So that's why I'm a few minutes late today. Yeah. But I have no pre-requested questions, which means Raj, whatever you want to hit, whatever you want to talk about, I am down. We can do it. So totally, I am. If you hear the clinking of keys, I'm just gonna be moving through a few emails. But whenever you're ready with a question, I am ready to dive into it. Oh, let's see. Let's see. You're reading the book and realize that a lot of things are in the beginning. Yeah, absolutely. And I'm assuming you're talking about what we're doing right now in Gen Chem is like the beginning of the organic chemistry book, and that is totally correct. I think I've said it in our Gen Chem at one point that the most important part of Gen Chem for organic chemistry is like the hybridization stuff, intermolecular forces. Okay. So valence bond theory. Okay, here let's dive right in here. So. So actually, valence bond theory is the official name of hybridization. All that hybridization stuff that we've been learning is valence bond theory. We haven't called it that in Gen Chem, but that is what it actually is. So So anyways, if you understand or feel like you have a grasp on hybridization, then then you're actually doing okay with valence bond theory. It's just the idea that in order to form bonds to make molecules, that the atomic orbitals hybridize, combine to make to make new hybrid orbitals that then engage in bonding through direct orbital overlap. So that's basically it. And if you can identify sp2 hybridization, sp3 hybridization, sp hybridization, then you've got all the valence bond theory you need to do sophomore organic chemistry. So yeah, that is that. And it's not too shabby. Okay, do you want me to like try explaining it from a different like perspective? What about it in particular do you not understand? Like what part about it? Like do you understand what how a sigma bond's made through direct orbital overlap? Does that part make sense? Okay. Okay, so none of it at all. Okay. Well, let's try this. So consider H2. All right? Which is hydrogen. All right, the hydrogen atom. I could ask you to draw a Lewis structure for this guy, right? And you could handle this. You could do this no problem. If I asked you to draw the Lewis structure for hydrogen, you would draw it like this. Right? That's the Lewis structure for H. No big deal. You got this so far, right? Now the question that I want to ask is how does this bond form? All right, I want to know, how do these two hydrogens take their one electron and each share them together to make that bond? How does that bond form? And the answer goes like this. So we're going to have one hydrogen which I'm going to color blue. Now we know the electron configuration for hydrogen, right? Is 1s1, and that means that there is one electron sitting in a 1s orbital. That's our first hydrogen. Now our second hydrogen also has one electron in its 1s orbital, right? Yep. Okay, totally. Yes, absolutely. Oops. Absolutely. All right. We each have an individual hydrogen atom that has one electron sitting in its s orbital. And they're, like you said, they're each looking for another electron. Now, what these two molecules are going to do is they need to move towards each other. They need to move closer. All right? They need to move closer so that, all right, I'm going to draw a picture. So these two are moving closer. They need to move closer so that their orbitals, the 1s orbital of the first hydrogen, I'm not happy with that one either. Okay, that one's pretty good. The 1s orbital of the first hydrogen overlaps with the 1s orbital of the second hydrogen, so that the electron from the blue hydrogen is actually in both orbitals, and the electron from the red, salmon, orange hydrogen is also sitting in both orbitals. All right. Each 1s orbital smushes together to create a new orbital, which is made out of the two atomic orbitals, and that holds the two electrons. Are you with me so far? All we've done is we've moved our 1s orbitals to be overlapping, to be occupying the same space, so that both electrons are in the salmon 1s orbital and the blue 1s orbital simultaneously. Are you tracking so far? Okay, so now get this. When this happens, when you kind of take your two orbitals and smush them together so they're occupying the same space, so that the two electrons are each in both orbitals simultaneously, this whole thing has a name, and this is called direct orbital overlap. All right, that is the name for that thing. It is called direct orbital overlap. And direct orbital overlap makes a type of bond known as a sigma bond. All right, so whenever you have two orbitals smushing into the same region of space so that their electrons can be shared together, that is called direct orbital overlap, and it leads to the formation of a sigma bond. Are you still tracking? Awesome. Awesome. Okay. All right. Excellent. Now the big take home, the thing you want to remember is every single bond that we've drawn in every Lewis structure, one single bond is one sigma bond. All right? Every single bond you've ever drawn is a sigma bond. It's created through direct orbital overlap. Yeah, exactly. And that is a sigma bond. Are you ready to hear about pi bonds? Is the S because of sigma? What S? Oh. Gotcha. Yes. Ish. So sigma bonds form anywhere there is direct orbital overlap. So hybrid orbitals can form them too. Yep. And pi bonds come from p orbitals, which is why they're named pi. Totally. So, question. All right, solid. Okay, so let's talk about pi bonds. All right. So, now, with a pi bond is a different type of bond. So let's consider something straightforward or simpler. Let's look at the molecule O2. All right, molecular oxygen. If you draw the Lewis structure, for oxygen, it's going to look like this. All right? And, excuse me. If you look at the hybridization for oxygen based on the number of electron groups in this atom, this oxygen is attached to one atom, and it has 2 lone pairs, which gives us 3 electron groups. And whenever you have 3 electron groups, that means you're dealing with sp2 hybridization, right? Whenever you have a trigonal planar electronic geometry, then your hybridization is sp2. Now let's take a look at the bonding system between our 2 oxygens. All right. Now our first oxygen, all right, has a couple lone pairs on it. All right. And we know it's bonded, double bonded to that second oxygen, which again I'm going to draw in this kind of salmony color. All right, a couple lone pairs, and we're double bonded. Now we know how to make that first bond. We overlap our sp2 hybrid orbitals together so that the electron from each is sitting essentially in both orbitals all at once. All right. It's the salmon colored electron and the blue electron are both inside the blue orbital. The blue colored electron and salmon colored electron are both inside the salmon colored orbital. So this is our sigma bond. All right. Now the question is, where is the other bond? All right. You can only ever have one sigma bond because we've made a new bonding orbital, right? We have 2 electrons in it, and we know that 2 electrons are all that fit in an orbital. So the double bond, the electrons in the double bond have to be somewhere else, and that is where your unhybridized p orbital comes in. On both the blue oxygen and the salmon oxygen, we have an unhybridized p orbital. All right. This is here because our sp2 hybridization left one p orbital out of the hybridization scheme, right? So sp2, whenever you're sp2 hybridized, it means that you have made 3 new hybrid orbitals out of 1 s and 3 p's, right? You've got your 3 sp2 hybrids, but you also have 1 unhybridized p orbital, right? And that's pz. Now, it is not possible for these 2 p orbitals to engage in direct orbital overlap. There's no way for them to touch each other, to move the lobe of one orbital into the same space as the lobe of the other orbital. Direct orbital overlap is not possible. What is possible, however, is something called indirect orbital overlap. What happens when you have 2 parallel p orbitals is this. Your 2 parallel p orbitals merge through something called indirect orbital overlap. All right. Indirect orbital overlap to form a pi bond. All right. And when we talk about indirect orbital overlap, when you have these two parallel p orbitals, so I just picked PZ. So you can totally use PX, PY, or PZ to do this. I use PZ because it's easiest to draw. Yes, and this is where the tunneling thing comes in. So I said indirect orbital overlap. What happens when you have two parallel p orbitals is they start blurring together, both above and below the sigma bond. And the barriers between these orbitals dissolve, allowing the two electrons to meet in the middle. So we have our two electrons chilling together. We've got a shade, half of our pi bond. And yeah, so together, the top and the bottom are the two lobes of one pi bond. All right. So this is called indirect orbital overlap because the two orbitals don't directly overlap into the same space, but they exist parallel to each other and they kind of blur together in this different new way of bonding. All right. And so what we have called up to this moment a double bond. One double bond is equal to one sigma bond together with one pi. When you have them both existing between the same molecule, that one sigma together with one pi is what we've been calling a double bond. Ah, no. There is only one pi bond. One pi bond has two lobes. You can think of it like this. Every pi bond, has an upstairs and a downstairs. But it's one pi bond. Just like a two-story house is one house. Totally. All right, so that is indirect orbital overlap, and that is how pi bonds form. Oh, no, don't apologize. Okay. Let's see. You know that one. Oh. Okay, so I know that we have. Yep, exactly. The hybridization will tell you. Because we're sp2, very good question. And the answer to that is actually no. But so not 100% of the time. But every time you see, oh, hang on. There we go. Every time you see a double bond, it will be made out of 1 sigma together with 1 pi. The reason why I wasn't willing to commit Vraj to 100% of the time is there is a very notable exception. If you draw the Lewis structure for the molecule BH3, the Lewis structure comes out looking like this. There's no other way to do it. And if you look, we've got 3 atoms attached to our central, 0 lone pairs. So that means we have 3 electron groups. And whenever you have 3 electron groups, your trigonal planar and your hybridization is sp2. So boron in this molecule, this atom is sp2 hybridized. But as you can see, there are no pi bonds here. So sp2 hybridization usually means there's a pi bond, but it doesn't guarantee it. That being said, having a double bond guarantees a pi bond. Let's see. Yes, yeah, totally. It depends upon hybridization and bonds. If you're gonna have a pi bond, you need to be sp2 or sp hybridized, because you need that unhybridized p orbital. But whether or not you have a pi bond depends upon, do you have a double bond in the system or a triple bond in the system. Totally. Totally. How are you feeling now? We sure can. Are you after an example where you need to like draw the bonding orbitals, or what did you have in mind? Okay, sweet. All right, so here let's do let's do this example. Let's draw let's see, let's draw the 3D representation of the bonding orbitals in, let's do nitrogen. All right, so step number one, let's look at our hybridization here. So we have one atom, and we have one lone pair, which means we have two electron groups. And when you have two electron groups, your electronic geometry is linear, and your hybridization is going to be sp hybridized. All right? So that means that we have two. So for sp hybridization, we have two sp hybrid orbitals. Whoa, that is an ugly p orbital. That is an ugly p orbital. Can I get my stuff together? There we go. It's better than the other two. There we go. That's a good p orbital. For sp hybridization, I like to use pz and px because I think they make it easiest. All right, so now nitrogen, each nitrogen has a lone pair. All right, and we're here. We're going to have the direct orbital overlap of our two sp hybrid orbitals on each nitrogen to form our sigma bond. All right, so that's our sigma. Now here we're dealing with a triple bond, all right? We're dealing with a triple. So we formed the first part of our triple, right? We've got 3 bonds to make. Our first one is made through direct orbital overlap with our hybrid orbitals to make that sigma bond. Next, we need to form our second bond, or our first pi bond, through the indirect orbital overlap of 2 of our unhybridized p orbitals. So you do that by drawing the 2 p orbitals and then connecting them, kind of blurring them together. All right, now half of this thing is shaded. We have the electron from each one. They get to meet in the middle, and that is our first pi bonds. Not quite. In every multiple bond, there is always 1 sigma the rest will be pi bonds. There can only ever be 1 sigma bond because once you make that orbital holding those 2 electrons between the nucleus, there isn't room for any more electrons sandwiched between the nucleus like that. So there will only ever be 1 sigma bond. Yeah, totally. So here, we've got our 1 sigma bond right here. This guy's our sigma. And then we have also formed our first pi bond, both above and below that sigma bond. Yes. Yes, there are. Yes, there are. There are 2 sigma bonds in 1 molecule of water. But there is only 1 sigma bond between each pair of atoms. Whoa. Atoms. Atoms. Right, so water, the molecule water has 2 sigma bonds, but between each oxygen and each hydrogen, there's only 1 sigma. Only 1 sigma fits between 2 atoms. But in a molecule with multiple atoms, you can have multiple sigma bonds. So how do you feel about N2 so far? Whoa. Yeah. Let's see. So since it's a single bond, there's 1 sigma. Yep, absolutely. That is absolutely correct. Because there's a single bond, there is a sigma and no pi. Totally. If it were a double, it would be a sigma and 1 pi. Or if you have a triple, like we do here, that would mean it would have to be a sigma plus 2 pi. All right, let's do this. Okay, so far, let's look at what we've done. We've made 2 bonds, right? We've made 1 sigma between our 2 nitrogens and 1 pi. And when you look at the orbitals that we've used, the only orbital left is our px. And px is perpendicular to the plane of the screen. So, excuse me, the p orbital here, oh, that's kind of ugly. Let me try that again. The p orbital here is, no, I don't want to do that either. All right, that's pretty good. Going out in front and back behind the plane of the board. Now, to show that it's coming out in front, the blue p orbitals on both of these nitrogens are blocking out the lobe, that bottom lobe of our first pi bond. All right, so that's why I'm erasing right there, so it looks like the perspective is on point. All right, now these 2 orbitals blur together through indirect orbital overlap, both in front of and behind the sigma bond. All right, their 2 electrons get to meet in the middle. See, our back lobe is going to end up being shaded. And this is our second pi bond, the 2 lobes of our second pi bond. So here, in the molecule of N2, we have 1 triple bond, which is made up of 1 sigma plus 2 pi bonds. Altogether are the individual pieces that make up that triple bond. Awesome. Awesome, dude. I'm so glad we were able to connect on this business. Because it really is like foundational, especially for moving on into organic chemistry. This is like like you said at the beginning of the stream, it's like chapter 1 of any Ochem book. You're talking about this business. Oh, that is a great question. That is a great question. So it turns out, so all this hybridization stuff, right, is valence bond theory. Oh yeah, of course, of course. So valence bond theory, and this is me. I'm gonna get to your a question with about what about like 5 atoms? All right, valence bond theory works great is excellent as long as the octet rule is not being broken. In other words, valence bond theory is solid. This is a solid explanation. For the bonding seen in carbon systems. Where valence bond theory fails is with expanded octets. So it fails, however, to explain the bonding. Oops. Seen in expanded octets. So valence bond theory breaks down when you break the octet rule. It doesn't have good explanations for the bonding that we observe in those systems, and so it gets replaced by a competing theory that kind of has a different take on bonding called molecular orbital theory, and so its valence bond theory works in very simple cases but doesn't work for expanded octets. So you don't have to worry about drawing systems with 5 atoms or more attached to your central atom. I do want to say, before you hit me with your next question, that if you have 4 atoms attached, like we do in a molecule of methane, in this instance you would have 4 electron groups, which would mean that your hybridization is sp3. So, in other words, you have 4 sigma bonds. All right, sp3 is all sigma bonds. All right. Okay, let's take a look. So let's see. We're dealing with phosphorus pentachloride. All right, so let's draw our Lewis structure, or I'm actually just going to draw. Whoa, that's a sulfur. Straight to the geometry. So here, every chlorine, we would have enough to give every chlorine 3 lone pairs. All right, so this is phosphorus pentachloride. And let's see, the question is, the central atom of phosphorus pentachloride would be A, partially positive, B, partially negative, C, +3 charge, D, -3 charge. No, actually, a trigonal bipyramid. Yeah, totally. Trigonal bipyramidal. All right, so now, one thing you'll notice, so let's calculate the formal charge. All right, let's do our formal charge calculations for both phosphorus and for chlorine. All right, for phosphorus, when phosphorus is neutral, it has 5 electrons. And when you calculate formal charge, you get, trigonal bipyramidal. 1 electron per bond. Phosphorus in this structure has 5 bonds. So here phosphorus has a formal charge of 0. Chlorine, when it's neutral, has 7 valence electrons. Each chlorine in this molecule is the same. It has 1 bond, so that's 1 electron plus the 6 in lone pairs. 7 minus 7 is also 0. So when you look at, and for those of you who don't have your eye on the chat, these are the possible answers. Answer A, so this is for the central atom. In this question, they're saying the central atom is A. Let's see, what's A? Is a partial positive, delta plus. B, they say that the central atom is a partial negative. C, central atom has a positive 3 charge. Or D, that the charge on the central... Oh, well, hang on. That the charge on the central atom is a -3. All right. Now, what we just did, we calculated our formal charges. We see that our charge on our central atom, phosphorus, is 0. So we automatically know that D and C are wrong, right? It has no formal charge, so it's neither +3 nor -3. Now, what's this business about partial positive and partial negative? All right, and here, to answer whether it's partial positive or partial negative, we actually need to look at the difference in electronegativity between phosphorus and chlorine. All right, and so for that, we need to look up our electronegativity numbers. Now, chlorine, so for the difference in electronegativity, all right, that's what we need to look at. Chlorine has an electronegativity of 3 0.0, and phosphorus has an electronegativity of 2.1. It's actually the same as hydrogen. So the difference here in electronegativity is 3.0 minus 2.1, or let's see, the difference is going to be 0.9. And 0.9 is smack dab in the middle of the range of polar covalent. So we're dealing with a polar covalent bond, which means that each chlorine here has a partial negative and our central phosphorus, because it's less electronegative, has a partial positive. So the correct answer here would be A, because, yeah, absolutely, Viraj, yeah. Yeah, partial positive is correct. Because chlorine is more electronegative than phosphorus, and that means that the electrons in this polar bond are going to spend more time around chlorine than phosphorus. So chlorine picks up a delta minus, phosphorus picks up a delta positive. Yes, exactly. Exactly. That is 100% correct. That is correct. That is also correct. Polar groups are hydrophilic because water is polar and like attracts like. Non-polar groups are hydrophobic because water is polar, so it likes polar things. If it's non-polar, we call it hydrophobic because it's afraid of water. Totally. So between water and oil, which is which? Are you so we say that oil is hydrophobic because it will not mix with water. Water is kind of like the baseline by which all other things are judged. Ah, yes. Yep. Soap is an interesting molecule. It is philic. It's hydrophilic on one end. And hydrophobic on the other end. So it can dissolve oils. So you'll see this in OChem over and over, where we talk about different regions of a molecule. Like, oh, this portion of a molecule is hydrophilic. Yeah, they use soap to take off oil because, yep, exactly. It's like it is so cool. It's so cool. It's like a weird food chain. Soap dissolves oil. Then the water dissolves the soap. And that is how you get water to remove hydrophobic materials. Yeah, it's totally like EDTA with lead. Excellent analogy. Ah. Great question. Hydrophilic will hydrophilic portions will be polar will be polar or charged, or let's see, polar, charged, or able to engage in hydrogen bonding. Hydrophobic regions will, or I should say, are always nonpolar. And that's how you analyze a structure for its hydrophobic and hydrophilic parts. Oh, let's see. Um, uh, totally. Oh, I'm so glad. I think I might Sounds good, dude. I think I might link to this video in our Gen Chem Canvas because I bet there's a lot more in the class who could benefit from maybe a slower explanation of hybridization. Later, dude. Awesome. Well, if Raj is piecing out, that means that that all of our questions are dried up. So I think I'm gonna call. Yeah, I totally will. I totally will. I'm gonna put a pin in this here. It was fun, and I will catch anybody who wants to talk OChem on Monday. We've got 2 more office hours, and yeah, that's that. Thanks for tuning in. Thanks for watching, everyone who checks out later. I'll catch you next week. Later.